It's hot. Okay. All right. Now let's get the slideshow set up from current slide. I don't think I'm going to need the graph slide anymore. That's what's going to come up.
Well, you have a blank slide.
I know, but I've got to let it come up first. Yeah. Oh, I didn't turn that on. But the screen's blank anyway. Well, here it comes, finally. Well, I got halfway there. I have them now. Hide presenter view. What a pain in the neck. And by the way, all the YouTube videos are published and they are through the link. Okay.
So it's not like you can't do like integrity classes, or because when I got to work, I don't know, I can watch my work.
Right.
I just gotta wait till after I watch YouTube videos.
Yeah. Well. Okay. You know how you've gotten them. You've seen them. Yeah. You can watch them whenever you can. You're used to integrity.
Yeah.
Oh, does Alabama use it?
Oh. Well, not every class.
Right.
So.
Well, what am I doing? Our administration thinks it's too expensive, so that's why we're using this cheap version. It's a screen capture, but not nearly as good as integrity. All right, we finished all that we're going to cover in chapter 1. We covered the parts that were leading to matrices. Now we're backing up and starting with matrices, and actually some of this is pretty repetitive, but again, how we name matrices, we usually name them with capital letters. Capital A, capital B, capital C, whatever. This is in page 40, 2.1, very beginning. Then, once you have a matrix name, like we're going to have matrix, okay. So you have a matrix A. Its elements of A would then be, you could represent that just naming the matrix A, or giving the matrix bracket there and saying Aij. That represents all the elements in A. For all the i's, 1 through n, let's say, or m, whichever you want to call it, 1 through m, let's say, and j, 1 through n, that would be an n by n, m by n matrix. And that would be, those could be two ways of expressing that matrix, okay? And then the third way is actually drawing them out, okay? And that would be A11, A12, A13, to A1N, A21, blah, blah, continue, down till you get to AM, yeah, okay. Let's go to AM1, okay. So let all these continue until you get there. Okay, so you could express a matrix any one of these three ways. Capital letter, a bracket with the Aij, or expand that and list every one of those Aijs. Okay, now, what we're going to deal with in this are primarily real matrices. We're not going to have any complex numbers, only real numbers in the elements of the matrices in general. We may slip some in sometime, but for special cases. Okay, now, this is pretty obvious, I hope. What do we mean that two matrices are equal? Matrix A is equal to matrix, it's pretty obvious, it's equal to itself. It's supposed to be matrix B. Okay. It's a pain in the neck to do it this way. Okay. If those two are equal, what that says is the element Aij here has to be the same as every element Bij here. Now, what does that imply? Number one, they have to be the same size. Pretty obvious. If this is an M by N, this had better be an M by N. Okay? Gotta be. You can't talk about equality of matrix in your thing. So the I's and the J's must be going from the same one to M and one to N. Okay? But not only that, just being the same size doesn't work. The A73 has got to equal B73. You know, an A317 has got to equal B317. In other words, you have the same bingo cards. No, but sort of that way. So that's what we mean. Every element, as long as I and J are, the I's and the 2 and the J's and the 2 are the same, they've got to be the same size, and the corresponding entries have to be exactly the same. All right, so let's look at example 1. Pretty simple example of that. Okay. Here are 4 matrices. Matrix A. A real creative one. 1, 2, 3, 4. Okay. What's that? Yeah. B is a matrix 1, 3. C is a matrix 1, 3. Yeah. Oops. No comma there. And D is the matrix 1, 2, X4. Okay. Now, A equal B? Why not? Not the same size for sure. A equals C? No. How about B equals C? Well, they're close to the same size, aren't they? Same elements. M and N are different, yeah. One's a 2 by 1, the other's a 1 by 2. So no, they can't be. A and D, could they be equal? How? If X is 3 and only 3, okay? If that were true, they're equal. Any other value for X? No, they would not be equal. Now, let's go into a little bit of nomenclature here too. And let's see, there's a little side note there. Let's see what it says. The if and only if, when you see that in a statement, like a definition or something else, sometimes I'll write that when I'm writing fast. Oh, and you don't have a book yet, right? And you have one, okay. Sometimes I'll do IFF, if and only if. That's in the Navy, that's an identification friend or foe, but that's something else, okay? Another symbol is this one, okay? Sort of like A implies B, okay? This would be, or A is implied by B, okay? But if the arrow goes both ways, that means if one thing's true and the other thing's true, if and only if is going one way, only if is going the other way, then so sometimes I'll use either one of those notation rather than writing out if and only if. Yeah. So anyway, not that. Now, we have a special name. Well, we have a special name for all these. What's this called? Special name? Square matrix, okay? This is called a what?
Rectangle matrix.
Okay, it is. You're absolutely right. And this is too. It's just a square rectangle. Yeah, right. This is also a rectangular matrix. This has a special thing. It's a vertical column matrix, which is also a column vector. Okay? And this is a row matrix or a row vector as well. Okay, so these can be called two other things: column vector, column matrix, row vector, or row matrix. This is a square matrix, and then all matrices are rectangular. by definition. You can't leave off a corner or something like that. No. That's logic. It's circular. Never. Okay. So, now here's another one. What if we had two column matrices? One, 3, and let's call E would be a column matrix 2, 4. Now, we could, and those could also be called vectors, so we could call this B1, say, and they bold a vector. I can't write bold, so I put the little vector symbol over it. This could be called E1. Now, they threw in the 1, so you didn't need the 1s. You could just call it E. And if you did what they call a partition, then you could say, let's just take this one, B1 partition with E1, these being vectors. That then forms a matrix, and that would be matrix A, right? Because 1, 3, 2, 4, put them, partition them like this, and you've got your matrix A, okay? So they threw that in here. We're going to come back to partitioning much later, but they just threw that in here now. All right, let's now talk about operations we can do with matrix. In fact, that's what the whole section is. We talked about equality. Now, what are some things we can do with matrices? So it's a big pain in the neck to have to do this every time, but we do. Okay, we're going to talk about adding matrices. We're going to talk about subtracting matrices. And then we're going to talk about two types, but not now. We're only going to talk about one type of multiplication, but you have two types of multiplication. One is scalar multiplication of a matrix, and the other is actually matrix multiplication. Two completely different operations, very different operations. We don't talk about dividing matrices. We'll kind of get to something that's similar to that, but that's later. So let's talk about adding two matrices. To add two matrices, what is one requirement? They've got to be the same size, okay? And here's why. Because to add two matrices, let's say matrix A is this good old Aij, and B is another matrix Bij, where I and J's have the same limits, 1 to M, 1 to N, for both of those. That means they have to be the same size. Then the sum of those two matrices, A plus B, you add each and every element, corresponding elements together, Aij plus Ij. Okay, and you do this I from 1 to, say, M, and J from 1 to, say, N. Okay, if those are M by N. They've got to be the same size, and you add every element, corresponding element, as you go. Got to. Okay? If they are of different sizes, no way you can add them. Don't even try. So let's do example 2. Pretty simple example. Okay? -1, 2, 0, 1, plus 1, 3, -1, 2. Okay? Number 1, can you even add those two matrices? Yes. Since you can, what would be your result?
0, 5, -1, 3.
Got it. Okay? 0, 5, -1, 3. Okay, how about these two? Whoops, let's go to a clean page. Any questions on that before I lose the page? Okay. 0, 1, negative 2, 1, 2, 3. Add to that 0, 0, 0, 0, 0, 0. Can you add those two?
Yes.
Yes. Okay, because they're the same size. What's the result? The first matrix. You're absolutely right. 1 or 0, 1, negative 2, 1, 2, 3. Okay. Now, therefore, we can call that second add-in, or whatever you want to call it, the zero matrix. That's the 0, 2 by 3 matrix, or 0, 2, 3. They'll say them several different ways. And the zero matrix added, as long as it's the right size of a zero matrix, added to any matrix of the same size is always going to give you that first matrix, because the zero matrix doesn't contribute a thing. Not a trivial thing. It seems like it is, but it is indeed is. Now, how about this? 1, negative 3, negative 2. What kind of matrix is that? A column matrix or a column vector, and it's a, what would be its size? 3 by 1. So you can add to that any other 3 by 1 matrix, like this one. What does that give you? That gives you the zero matrix. Okay? So since those two add to be the zero matrix, we give those two a special name. These are called the additive inverses of each other. Just like 7 plus a negative 7 is 0. We say negative 7 is the additive inverse of 7, and vice versa, 7 is the additive inverse of negative 7. So we could actually also say, this would be, here's another way you could express it, negative of negative 1, 3, 2. We just basically factored out, though we haven't found that legal to do yet, but it is, plus 1, negative 1, 3, 2. That is always the zero matrix. But it has to be the same size, and this is a 3 by 1 zero matrix. Okay. Now, let's do one more. What's that? Yeah, because you're adding its inverse. Yeah. So that's exactly what you do. But remember, we only really subtracted back when we're only dealing with whole numbers and fractions, but everything always being positive. Once we introduce signed numbers, yes, you then add the opposite, add the inverse of it. And so from there on, subtraction is always pointless, okay, because you don't need, so like, how do you shoot a blue elephant? With a blue elephant gun. So how do you shoot a red elephant? No, you swing around by the trunk until he turns blue, and then use the same gun you already had. You know, there's no reason to go out and buy a new gun, okay? So the thing, that's subtraction. Yes. All right, never mind. All right, let's go to, and clear all that ink off. Let's try this one more. A 2, 1, 0, 4, 0, negative 1, plus, is a plus, 0, 1, negative 1, 3. Cannot do it. Exactly. Don't even try. Okay? Can't happen. Undefined. Okay? Now,
how do you, are we going to have problems like that, like on the test?
I hope not. That's just too simple. Right.
Okay.
Yeah.
I mean, I'm just like, I don't know how you do undefined.
Yeah, I just say UND. That'll do for me. I write it out. I don't care. I can usually figure out. All right. So now let's talk about multiplication, but we're going to do the simple one first. We call it scalar multiplication. If you have some matrix A, which is defined as Aij, where ij are going from, say, I is going from 1 to m and j is going from 1 to n. Okay? So that makes it an m by n matrix. Okay? And C is a scalar.
The scalar is when you just take whatever your scalar is and multiply every element in the matrix.
That's exactly what we're going to do. Scalar is a number, any real number. It can be a positive number, a negative number, a fraction, a decimal, rational or irrational. We're just not letting it be.
And the reason it's called a scalar is because a lot of matrices are counting as vectors.
Yeah.
So that's
Like a 2 or so many dimension
so
matrix.
that'd be a scalar and a vector. Just
Right, exactly. It scales it up or scales it down or scales it some way. Okay? That's why they call it a scalar. But it's just a number, a real number so far. Okay? Then the scalar multiple of A is C times A, and this is exactly what you would be saying, would be the matrix that you multiply every Aij, everyone, by that same scalar C. Okay? That means not just one row or one column, it's every element in there gets multiplied by that C. Okay. Now, later when we do other things with matrices, we see that that scalar multiple can really blossom and have a big effect. Okay? So this is what we mean by scalar multiplication. Okay. And then this also leads the other way. This equality, remember, goes both ways. So let's say they give a little side notes here, since you mentioned a fraction. Maybe you're looking at your book. 1/2 negative 3/2, 5/2, I'm sorry, and 1/2. That's a rather awkward matrix to write. What's a simple way to write it using this in reverse? Pull out the 1/2. And that would leave you with
1, -3, 5, and 1.
exactly. Okay? And those are exactly equivalent.
Why would you use a scalar there?
What's that?
Why would you use a scalar instead of pulling out
1/2 is a scalar.
Well,
Yeah.
Well,
Well, I didn't understand what
he's
you're
saying,
asking.
why didn't you just use 2?
right. Why did you just multiply by 2 and write it out?
Okay. Multiplying by 2,
It's adding something to it.
Oh,
yeah, it's changing it.
Matrix.
This is the same.
Okay.
Now, multiplying by 2 would have produced something else that's the same, but it's not the same thing. If you did 2 by that, then that would be 1, -3, 5, 1.
But not with the scalar.
Yeah. And those two are equal, okay? Because this is just scale. But that isn't, this scales to this, and that scales to this, you might say, because,
I follow.
I see what you're asking. Okay, so let's do a few of those. And again, this is pretty simple stuff, but it can get more esoteric pretty quickly. It won't yet, but let's do it. Here's two matrices. A. 1, 2, 4, -3, 0, 1, 2, 1, 2. Used to be a defense we ran in basketball. Okay. Here's B. Bless you. 2, 0, 0. 1, -4, 3. And -1, 3, 2. Hope I copied it right. All right. A here. Find 3A. B. Let's see. I think we can just. This This is such a pain to do. Okay. All right. B we'll do is minus B, and C is 3A minus B. Okay. Can you tell me what 3A is?
3, 6, 12, 8, 9, 0, 2, 6, 36.
Okay. Wasn't keeping up too well there, but I guess got it. What is negative B? Negative 2. I hope you said. I can't hear well, but. And what would 3A minus B be?
1, 6, 12, -8.
Whoops. Negative 10, isn't it? Yeah.
-4.
Okay, was that 4?
You're adding it to the negative B already. You're adding that 3A to our negative B.
Yeah.
Wait, okay.
Yeah. You can go back and do all that work over again, or just notice that is
Already
this one plus that. Yeah.
Does that be 0 for the next one?
And you said 0 is the next. And 7. Huh?
0 again?
0, 4, right? Is that what you get? 1, 6, 12. Negative 10, 4 is. Whoa! Yeah, there's. I got something wrong here.
Yeah, that's why I'm trying to figure out what y'all do. Like, what? And -9 minus -1 should be -8.
No. You're adding
Negative
it
9
to
minus
the
1. Negative 9 minus 1 is negative 10.
But you're subtracting
No.
a negative.
Okay.
The matrix is now negative B, so
Right.
you're just adding.
This is negative B.
Oh, okay.
Right,
Okay.
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 There's B. So if you're going to use B, then it's.
No, I got what you're saying now.
Right.
But it is supposed to be -4.
Okay, is it? That's what I. No.
Because you're supposed to be adding that. So it would be -10, negative.
It'd be 0
This
plus
is,
4.
okay. B was that, so the negative of that, this is a 4.
Okay, we got 4 already. Okay, see, I thought it was -4 and negative.
Yeah. Now, what I can't quite figure, I think they made a mistake in the book.
Where does that happen different?
On that last one,
-6.
I copied the problem wrong. That's where it was. That's supposed to be in a -1, so that's a -3, and that makes this a -6. It always helps to copy your problem right. Okay. All right. That was the only part I came up different. I went, whoa. Yeah. Yeah.
We got road in the last column.
What's that?
Is that a 2 in the last column? Or
Yeah,
Yeah, this one right here.
what up? No, in the
in the answer.
In the answer. Oh, that's a 6.
one or last.
First column, last row.
First column, last row.
That's a 2.
That's a 7.
Or that's a 7. Excuse me. That
6
looks like
and 1.
a 2.
7.
Yeah, that's what I'm saying.
Oh, I
That's a
see.
7.
Yeah, I slash my 7s, and I also get really sloppy with them. But actually, the other part is the page cuts off at the bottom. So let me clean that up a little bit too. Okay. Oops, it wasn't a negative, it was a positive. I don't know where that came from. All right, got it. All right. Now that was a little, they took some of the work out of it by just making you, this wound up adding those two together. We didn't have those two parts then, we did 3 times that minus that, and we worked it all out. But you should have gotten the same thing. Okay. And I slash my zeros too. And sometimes they look like 4s. What's that? And my Z's. I slash Z's. I was in the Navy and you were required to do that, so I got so used to it, I still do it. All right, now we'll move on to matrix multiplication. And they do give a, I don't really care sometimes for all their little games they play. Well, let's work through this and see why you would do something like this. But this one's not too bad. Here we have a matrix, and this matrix represents the rows stand for your stands in your stadium. This would be your south stand, your north stand, and your west stand. Okay? And then these are your concession stands. You have these concession stands outside these stands. So you're selling 3 objects there. You're selling peanuts. You're selling hot dogs. And you're selling, this must be from the north somewhere, sodas. Down here they're Cokes. Okay, no.
Hey, it's better than pop.
Or pop. Yes, exactly.
I say pop.
Pop, is that right? Okay.
It just makes my brain bleed a little.
Okay. So, sodas. Okay. Now, these are the number of items sold. 120 in the south stand, peanuts. 250 hot dogs sold in the south stand. And 305 sodas sold in the south stands. On the north stand, you sold 207 bags of peanuts, 140 hot dogs, and 419 sodas. There, the north stands have the southern sun on them, so they're hot. Yeah, never mind. You wouldn't know about that. In the west stands, they don't have much going on there. 29 bags of popcorn, 120 hot dogs, and 190 sodas. Okay. Now, if you happen to have another matrix, this being a column matrix, this is the price, the selling price of your peanuts, your hot dogs, and your sodas. Okay? The peanuts are selling for $2 each. Not peanut, but bags of peanuts, I guess. $3 for your hot dogs and $2.75 for the sodas. What a bargain. Okay. Yes, exactly. Okay. All right. Then, if you were trying to calculate, you were the vendor who had the contract for running these things, how much money did you make and where did you make it? Well, in the south stands, you sold 120 peanuts at $2 a bag, 250 hot dogs at $3 a pop. So I know that would be the third. 305 sodas for $2.75 a pop. Okay. I got you put in there. Okay. So, and then you do the same for north and west. Okay. See how that would work? And that would give you, if you did that, then that would give you a product. And if you not only multiplied, but added as you went, then you would have the south stands made how much money, the north stands made how much money, and the east stands or west stands made how much money. If you multiplied each of those out and added as you went. Right? That's what matrix multiplication is. Not scalar multiplication, but multiplying one matrix by another matrix. Now, admittedly, this is just a column matrix. but you could expand it and have top matrix. But notice what you're doing. You're multiplying the row here by the column there and adding them as you go. That's matrix multiplication. Okay? And they actually
A little bit more to it than
a little bit more than just multiplying equivalent things. A couple of things. Number one, does the size matter?
Well,
That was a trick question. Not in the same sense addition does. They don't have to be the same size, but there does have to be something in common.
Don't the rows have
Yes,
columns
yeah.
or something?
This is an
number of columns have to
yeah,
match the number of
an M by N. This has to be an N by something. Okay? If it wasn't, you can't do it. So the size does matter, but not in the same way for vector addition. Matrix addition. And then, with this being a 3 by 3, that's the size here, and you multiply it by, what size is that one? 3 by 1. What size is your result? Number here. Here's the deal. These two have to be the same, and then you get rid of them, and your result is a 3 by 1. And that's how you determine the size of the n. And we could do that. It's a little messy. 120 times 2, 240 plus, that's 750, right?
240 times 500, 740.
Okay, but this is a 3 here. That's
Oh. I
750.
thought we was, okay.
Yeah, 240 plus 750 plus, well, I can't do that with my head. So pull out your calculators and pop along. It works well because rules of order of operation keep you in check. And whatever you get from this row by that column, that's that entry, the first row by first column entry, the 1 entry here.
So it'd be like $1,828.
Okay, when you added them all? Okay.
Yeah, so
Say that again, 1828?
Yep, 0.7.
1828.75. Okay, do the second one. 207 times 2 would be 414 plus 520 plus, and you do that last one. Okay. I ain't about to.
You're going to take our word for it and say 1986.25.
1986.25, okay. And then the poor little West stands, that'd be 58 plus 360 plus whatever, 940 even? 0.50, okay, 50, okay. And that would be the money you made on the West stands. And then add them together and you get how much money the whole thing makes, but we're not doing that with the matrix. Okay, now, here's the other thing to notice. We notice the sizes, 3 by 3 by 3 by 1. These middle two have to be the same. If they are the same, then when you multiply, your answer is going to be the outside ones, 3 by 1. Here's the other thing. First row by first column gives you the 1 entry here. Second row by first column gives you the 2 entry here. Third row by first column gives you the 3 entry here.
And then you go to the next column.
Then you, yeah, exactly, right.
What?
Yeah. Simple math, adding and multiplying and adding, but just lots of it all piled together. Okay.
So just, for instance, that 3 matrices being multiplied together,
Yeah.
do like the first 2 and then the product of that last one?
Okay. Yeah, you would have to ensure that the size is right to make any of it make sense. And if they were, then it really didn't matter which order you did. And we'll see that coming up in just a minute. Your question, I think, was, is matrix multiplication associative? Is that what you're saying? So we'll see the answer to that. In general, yes, okay? But everything has to be lined up so it will work. So here's a definition of matrix multiplication. Normally, I don't think I would write it out, but since you don't have a book, let me do it. and it's going to be messy. So here we have A is Aij, okay? It's an M by N matrix, okay? So I is going from 1 to M, J is going from 1 to N, okay? B is a B, and it sort of aggravates me, they also call this IJ, okay? I would want to change those two because to me the I would have to be the same. They're not in this case. This is an N by P matrix, okay? Meaning now the I's are going from 1 to N and J's are going from 1 to P. So if you're going to do that, use a different letter, okay? So you don't say those are the same, you know, but they really, it doesn't matter because they're just counters in your summation, but it's, so now the product then, AB, okay? First, can you do that multiplication? Yes, the reason yes, because the second one here is the same as the first one there, so you can wipe those out, and what's the size of this? It'll be an M by P matrix, okay? That's the first part. So it's going to have, and again, they're going to name its element little c, and the ij's here. The I is going from 1 to M, and the J is going from 1 to P, okay? Now, and that Cij here, now to me, I'll write this down, and K equal 1 to N, okay? A I K times B Kj, okay? Which means when K is equal to 1, that's AI1 B1J plus AI2 B2J plus ... all the way up to plus AIN BNJ. Okay. That's how you do it. Now, to me, that doesn't say a lot. I mean, yeah, I can follow it, but mostly I figure out what I want it to say, and yeah, I can make that work. Okay. And it does work. But let's actually do one. It's much, the numbers to me are much easier to mess with than the generic form. Okay. So here's going to be our matrix A. -1, 3, 4, -2, 5, 0. Here's matrix B. -3, 2, -4, 1. First question, can you multiply AB? A times B. Why? This, yeah, the number of columns of the first is equal to the rows of the second. In other words, this is a 3 by 2. This is a 2 by 2. You can multiply them because the innards are the same. The answer is going to be the 3 by 2. Okay? Now, 3 by 2. Okay? Now, how do you do these? I do it this way. I first identify it's going to be a 3 by 2. I won't do this forever, but I do. So that means it's going to have 3 rows and 2 columns. And for now, that's how I suggest that you do it. Those are the spaces. You got to fill in the spaces. Okay? What is the entry here? This is the
1, 1.
1, 1 entry, so you use the first row here by the first column there. That would be
3 plus -12, which would be
-9.
-9. First entry is a -9. Okay? Which one you want to go to next?
Second one in that.
So the 1, 2 entry. So you use first row again, second column.
-2 plus 3, which is
1. Okay, very good. What you want to do next?
1 below 9.
Okay, so that will be the,
Second row, first column.
okay, so it's second row by the first column.
-12 plus
4, -4. All right. Everybody see it?
We can go ahead and do that last one of that column. So row 3, column 1.
You want to do row 3, column 1? Okay, that's fine with me. Row 3 by column 1, 3, 1.
-15.
-15. I see why you're doing it. You're just lazy. You saw that 0 there and want to take advantage of it. -15. Okay? What you want to do next?
Row 2, column.
Column 2, 2, 2. Okay? So it'd be row 2, column 2. That would be
8, and that would be
6. Okay? Everybody see that? And you don't have to jump around like this. You can do it in an orderly fashion if you prefer. And the last would be the,
the row 3, column 2.
okay, so you do row 3 by column 2. And that would be 10. Okay.
See, I don't know, I'm pulled to do it one column at a time.
That'll be fine. You can do it any way you want to. You just keep up with your own bookkeeping. That's the important part in linear algebra, keeping up with the bookkeeping. Okay? Which is sort of redundant, isn't it? Okay, -9, 1, -4, 6, -15, 10. Got it. Okay. Now, while we're here, let's do B times A. No, you don't want to do B times A? You can't do B times A. That'd be a 2 by 2 by a 3 by 2. You cannot do those because those are not the same numbers. So there's another thing. You're asking about kind of getting toward whether matrix multiplication was associative, but number one, it's not commutative. AB is not equal to BA in general, okay? Because a lot of times you can't even do it.
Unless they're square matrices.
Now, square matrices, you could do it. Do you think they're going to be equal then? We'll see. Okay? Generally
No,
not.
because there's adding in there.
Huh?
There's adding. Unless they're
Yes,
the exact
exactly.
same, or one of them's a
And
zero
you're
matrix.
adding different things at different times, yeah. In general, no.
Or if one's a zero
If one's a zero matrix, then it doesn't matter. Yeah.
matrix.
But there is another situation in which they are equal, and that's a special case, and we will focus on that when we get there. And that's a nice, important case too. Okay. Oh, and by the way, on that page, you don't have a book, there was a little blurb there on Arthur Cayley. And some little interesting information there. But he was one of the developers of matrix algebra. American father-son team, Benjamin and Charles Pierce, were also credited working with Cayley, or maybe not with Cayley, but so anyway, that's how we do matrix multiplication. Now,
Here we go. Discovery box.
yes, the discovery time. So let's clear this. And these are two pretty simple matrices. A is 1, 2, 3, 4. Really clever matrix. And B is a 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2. 0, 1, 1, 2 Okay? Let's add these two. A plus B. Want to tell me what that is?
1, 3, 4, 6.
Okay. How about doing B plus A? 1, 3, 4, 6. Now, you think you can generalize that? A plus B is always going to be B plus A. As long as they're the same size, then you can add them in the order, it doesn't matter. Because each of those elements is being added, and each of those elements is a real number. The order of adding real numbers doesn't matter, so you're fine.
As long as it's
Fine, period. Okay? Addition of matrices is commutative. Okay? How about calculating for me what AB is? Can you even do that?
yes.
Yes, you can. And what would it be?
So 1, no, that'd be 0
Mm-hmm.
plus 2, so that'd be 2 for the first column, first row.
Okay. And what did you say the answer would be?
2.
2. All right. Okay.
Nothing's wrong.
Yeah, okay.
Because it'd
Yeah,
be
2.
1 times 0.
Yeah, got it. Okay.
One to write it as
I'm sorry?
5.
5? Okay, you're going across? Yeah. Okay.
0, 4.
4. 11. Okay. Can you do BA? Yes, you can. So let's do it. I like to actually do it here, because I'm used to looking at them next to each other in that order. Okay. You don't have to, but why not? Okay, so I think we can stop right there and say these two are not going to be equal. But let's go on and do it just for fun.
And then the one below that would be 1 plus 6, which is 7, right?
All right.
And start up the next column. The 0 plus 4, so it'd be 4. And then the last space would be 2 plus 8, which is 10.
Anyway, anything you want to generalize from that?
Nothing at all.
Yeah. Multiplication of matrices is in general not commutative. In general, it will not be commutative.
Unless it's a 0.
Well, zeros, yeah, it would be, but there is another special case where it is commutative, and we'll get to that. That is, and it's non-zero, by the way. Okay.
Maybe all 1.
So, matrix addition does seem to be commutative, and matrix multiplication is definitely not, except in 2 special cases, multiplying the zero matrix or one other type. Okay, we'll get there. So let's do example 6. Whoops. Example 5. Sorry, I can't read. Okay, I hit the wrong button. All right. Here's a matrix multiplication problem. 103, 2, -1, -2. Try multiplying that by -242, 100, and -1, 1, -1. Okay, I hope I copied it right this time. Okay. Number 1, can you multiply those 2 matrices? Why?
Because it's 2 by 3.
This is a 2 by 3, this is a 3 by 3, and because those middle numbers are the same, you can wipe them out. Your product is going to be a 2 by 3. 2 rows, 3 columns. So I like to go on and put those spaces in there. I don't like to, but I do it for instructive purposes. And what is...
In this case, it might be better to do the rows
Okay.
Do it
What?
over.
Okay.
Stay with the same thing.
Which one you want to do first?
Well, one's a good place.
The one is a good place to start. So you use first row by first column, and that would be
-2 plus 0 plus -3 is -5.
-5. Perfect.
Okay.
And then what you want to do?
Column 2.
1, 2. So it'd be row 1, second column. That'd be
4, 0, 3. So
7. Perfect. And
the last one, row 1, column 3.
2, 0,
-1.
-1. Perfect. Next.
Row 2, column 1.
Okay.
1,
Second.
big 1.
Total.
Wait.
Okay. You said second row, third column. First column.
Oh, yeah. So it'll be -2.
-4.
Oh, yeah, sorry. I was looking wrong.
Yep.
Okay, -4 minus 1 is -5. Plus 2 is -3.
Okay.
20 now.
All right. Next.
Okay, so row 2, column 2.
Okay.
8 plus -2, so it'll be -6.
6. Okay. And
2, column 3. So 4 minus, wait, is that a -1 right there?
yeah,
That is. Okay, so that'd be a +2. So it'd be 6.
6. All right. All right. How did they do? -5, 7, -1, -3. Oh, -3, 6, 6.
I got a negative.
Oh, okay. I didn't write it. Okay. Sorry. Yeah. -4.
Man, just been your pen.
Minus. Yeah. -5 plus 2. Yeah. -3. Got it. Okay. I think we can do the next one under here. 3, 4. -2, 5. Ah. Such a pain in the neck.
Right over.
Yuck.
Back it
All right. -2, 5. Multiply that by 1, 0, 0, 1. Okay. Can you multiply those two? What are they? 2 by 2 by a 2 by 2, and that's going to give us a 2 by 2. Okay, I'll buy that. Okay, that'll be 2 rows, 2 columns. Where do you want to start?
Row 1, column 1.
Okay, and that gives you 3. Next.
Row 2, column 1.
Okay,
Be -2.
-2. Next.
Row 2, row 1, column.
Okay, what does that give you?
Column 1.
row 1, column 2.
Row 1, column 2.
Yeah.
What? What does that give you? Say again? 4.
4. And then row 2, column 2.
Okay,
Be 5.
5. What do you notice about that?
3, 4, -2, 5.
It's the same.
What you started with. So if you multiply by an entity by a special entity that you get the same entity you started with, we usually call that the identity element. Okay? And could you tell me anything about that thing we might consider
Reduced
being?
echelon form.
Okay, it's in row echelon form.
Or well, it's reduced row echelon.
Reduced row echelon form. It's a square matrix, right? And the main diagonal elements are all, and you got zeros everywhere else. That is called the identity matrix. We call it an I matrix. And then we usually give a subscript after it because identity matrices must be square. This one is. That one will be. It's a 2 by 2, so we call it I2. So if you multiply any matrix with 2 columns by the I2, you're going to get that same matrix. If this was a 7 by 2, multiply it by that, you get a 7 by 2, which is exactly the same. Precisely. It is called the identity matrix. I'm jumping ahead, but that's indeed true. That is B. Let's do C. Let me go to a clean page here. All right. C is 1, 2, 1, 1. I don't need a time sign there, but I'll leave it there for now. I wrote it. Okay, negative 1, 2, 1, negative 1. What's that? Okay, let's see if it is. Can you do it? Yeah, 2 by 2 by 2 by 2 is going to be a 2 by 2. 2 by 2 is going to be a blank, 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 blank. Okay, where do you want to start?
Row 1, column 1.
Okay.
Column 1, yeah, row 1, column 1. That would be negative 1 plus 2, which is 1. Or no, yeah, 1.
Okay. Yeah. 1? Is that what you said?
Correct.
Okay.
Row 2, column 1.
Row 2, column 1. We'll do that one then.
0.
0. Okay. Okay, you're doing row 1, column 2.
Right, yeah, and that would be 1.
Okay. Row 2, column. Okay. Row 1, column 2. Is that what you're doing?
Row 1, column 1.
Wait, row
2, column 1.
Yeah, row 2, column 1. Wait, no, row 1, column 2.
All right. Okay. Okay. Row 1, column 2. What would that give you?
0.
0. Amazing. And 1.
Something about the identity matrix, something.
Okay.
I get so turned around saying it out loud. Like, I could do it on paper, but then you're saying, like, row 1, column 1, and
Okay. Now,
7, 12.
here you have a matrix. You multiply by another matrix. You wind up with the identity matrix.
So it's an inverse.
Ha! Yes, that's what we call it, the inverse matrix. And here's something special about that. I probably shouldn't do it yet, but I'm going to do it now. Let's do this. Negative 1, 2, 1, negative 1 times 1, 2, 1, 1. What's that? You will. That do you do in general?
Well,
In this case, you will because it is an inverse matrix.
So if you multiply a matrix by its inverse, you get the.
You will, yeah, you'll get it no matter what order. This is that other special case I was talking about. In general, 2 matrices are not, matrix multiplication is not commutative. Like you said, if one of them is a zeroed matrix, that certainly makes it commutative. The other special case is if you multiply by its inverse. You'll always get it. And it doesn't matter which order you multiply, you will get the identity matrix.
So
2 inverse matrices, it doesn't matter the order, they're commutative.
So if you had a 3 by 3, you would end up with 3 by 3.
If you wound up with a 3 by 3 identity matrix, yeah, it wouldn't matter what order you multiply those either.
but these would have to be squared.
They always have to be square. To be an inverse, it has to be square, and to be commutative, of course, has to be square too. Both of them have to be square. Okay, that was jumping a little bit ahead, But let's now do the D one. All right. Oh, let's see. Can you even do this? This is a 1, -2, -3 by a 2, -1, 1. Okay. Now, first off, tell me, what do we call these two?
Row matrix.
Right?
Column
Column matrix or row vector, column vector. Either one, though we haven't, the book hasn't gotten there. What's the size of the first?
matrix.
1 by 3. Size of the second? 3 by 1. Can you multiply? Okay, you can. What will you get? A 1 by 1. You're going to get a single number. What will that number be?
Right, so you got, what is it, 2 plus 2 is 4, minus 3 is
1. It just happens to be 1. Okay. Now, can you do this? 2, -1, 1 by 1, -2, -3. What you think? Can you even do that? Why? This is a,
you have 1.
what's that?
3 by 1 and 1 by 3.
So yeah, you can. What will your answer be? A 3 by 3. Certainly not going to be the same, is it? Okay. And can you give me those entries?
That would be, right, so row 1, column 1 would be 2.
Right?
Row 2, column 1
Row 2, column 1. Okay.
-4.
Okay. Which are you doing?
Column 2, row 1.
Oh, column 2, row 1.
Go along with where you're.
Okay. Okay. Okay, you're going to do
Row 1, column 2.
row 1, column 2. Okay, we'll try that one. And what is that? -4? Okay.
And then the next one next to that is -6.
I'm sorry. -3. Okay.
6. Wouldn't that be -6, not -3?
Right. Sorry. I thought you said -3. I was just writing what you said. Sorry. Okay. You're doing 1,
Row
3.
1, column 3.
Yeah. -6. Is that what you said?
Yes.
Okay, I couldn't hear. Okay, wait.
6 is one of those quiet numbers.
-6. Okay.
Right, so row 2, column 1.
All right.
-1.
2, 3. Got it. Next. Got it. Okay. So certainly those two you can multiply, but you sure don't get the same answer. So it's not, for sure, not commutative because they're not even the same size. But you can do it. Okay. Now, going back to systems of equations, how are we doing? Okay, so far, time?
We have about a minute.
About a minute. Well, maybe we won't go to systems of equations. Okay? Then we'll start next time here, which means I'll erase this mark here. And we'll begin next time with here we go, systems of linear equations. Let's see, homework exercises, you can do 1 or 3. Any of the odds 5 through 11. Do either 13 or 15. And then do any of the odds 17 through 29. I think you can do any of the odds 31 to 37. And we'll stop there and pick up and go from there next time. All right. Yeah. I wanted to get the assignment on the recording before I started.